Great, thanks. Wow, it's great to be back in Chicago and back at GOTO. So I'm going to talk about effective microservices in a data-centric world, and I'll tell you a little bit about my background, the background of the company that I work for, and then apply that to some learnings that we've had in building out microservice architectures. So just to let you know where I'm coming from, I'm the VP of engineering of a company in San Francisco called Stitch Fix. And Stitch Fix is a clothing retailer that is sort of revolutionizing retail by turning it on its head. And we like to think of our combination of the business model as combining art with science. And if that doesn't make sense, that's fine, but it will in a couple of slides. Before that, I was sort of a roving CTO as a service, like my friends would call me. I was helping a bunch of companies scale their organizations, scale their technologies, and in large part, or in often part, the technologies involved adopting microservices and migrating monoliths to microservices. Before that, I was director of engineering at Google for Google App Engine. So App Engine is Google's platform as a service. And at the time I was there, it was the world's largest one. You might be familiar with Roku or some other platforms as a service. It's kind of in that same space. And then earlier in my career, I was chief engineer at eBay for about 6.5 years. During that time, I spent a bunch of effort helping to migrate eBay through a couple of iterations of their fundamental architecture. Cool. So I want to tell you a little bit about Stitch Fix, and this isn't to tell you that you should buy your clothes through our service, which of course you should, but it's basically to give you a background on the business model, because that will let you have some insight into why data is so important and why microservices are a good fit for what we're trying to do. So the business model at Stitch Fix is basically the reverse of standard retail. So rather than going into a store or into an online e-commerce site, you fill out a pretty detailed style profile about yourself. You tell us all the things you like, all the things you don't like, your price preferences, your style preferences, all sorts of information that you would tell maybe your friend or your sister or your brother for somebody who's going to choose clothes for you. So you give us all that information. We send you 5 hand-picked items in a box that we've selected exactly for you. And then you keep what you want and you return what you want. And obviously, you keep the things, you're going to pay us for them, but if you don't keep them, they come back for free and no problem. So behind that model is a lot of art and a lot of data science. So we made such an investment into data science that we actually have a 1-to-1 ratio between engineers and data scientists. So we have roughly 70 to 75 engineers in the team that I work on. We have roughly 75 data scientists in our algorithms team. And as far as I'm aware, this ratio is unique in our industry. I mean, I'd love to hear the counterexample, but so far, I believe it's the only company that sort of our scale that has sort of equal parts engineering and data science. And what do we do with 75 data scientists, right? Well, we actually apply intelligence to every part of our business. So we apply it to the buying process, which in retail is called merchandising. We apply it to inventory management, so we actually have physical warehouses, and managing the inventory there is done with data science. We do it we apply it to logistics optimization, so shipping out to get things to the people at the right time at the minimal cost. We do it for styling recommendations, which I'm going to talk about for the next couple of minutes. So the recommendations to the human stylists that actually choose the clothes that are going to go into the box for you. And we also do more standard things like demand prediction, trying to figure out how many clients we're going to have going forward, how many fixes or how many boxes in our terminology we're going to send out, that sort of stuff. And the key thing, though, across all those areas is that we have humans and machines augmenting each other. The humans wouldn't be able to do as well without the machines, and the machines wouldn't be able to do as well without the humans. So let me give you a quick example, working example of what we call styling. So styling is choosing those 5 items that go into the box for you. And we have about 3,500 human stylists that are all around the United States. They look at our inventory and and they choose the 5 items for you, and then they send them to you in the box, and we hope that you enjoy them. But actually behind that is a bunch of algorithmic work and a ton of data science. So as soon as you have signed up with the service with that detailed profile, we can immediately cluster you with a bunch of other customers that have similar tastes. And then we run a ton of machine learned models to make predictions about what you're going to keep and what you're going to return. And those algorithmic recommendations go into the interface that the stylists use to choose the things that we send. And then the stylist is not just taking the top 5 things that we recommend. The stylist is doing what the humans do best, putting together an outfit, deciding that this is a thing that a software engineer in San Francisco would wear, or this is something that a Manhattan socialite would wear, basically the things that humans are good at and the machines aren't yet. So for the rest of the talk, I want to talk about how we work at Stitch Fix, focusing mainly on the microservices. And I also want to talk about why that way of working actually works. So modern software development, to my mind, is sort of made up of 4 different segments. So and it's not just technology, right? It's organization, it's processes and practices, it's culture, and it's technology. And as far as I'm aware, or in my personal opinion, the ways that I like high-performing teams that I've worked in approach those problems in this way. So in organizations, we like to have small teams with well-defined areas of responsibility. For processes and practices, I'm a strong believer in test-driven development and continuous delivery. For culture, I'm a strong believer in DevOps, meaning that everybody owns end-to-end the services and applications that they build. And finally, I believe strongly in microservices. So I'm going to go through those first 3 super quickly to kind of give you a baseline, and then the rest of the talk is going to be about microservices, as I promised. So quickly on the small teams. So the high-performing organizations that I've worked in, sort of the Googles, the eBays of the world, do this. So they have small teams that are aligned to particular business domains. So a team has a clear, well-defined area of responsibility, and a team typically maintains a single service or application or a set of related services and applications. Teams are cross-functional, so within the boundary of the team, they have all the skill sets that they need to do their job. Now, I'm not saying they have all skill sets in the world, like we don't make our own hardware, we don't make our own operating systems, but all the things that the team needs to get their job done are all within the boundaries of the team. And of course, those teams depend on other teams at Stitch Fix for supporting services, supporting libraries, and tooling. On the processes and practices side, again, we're strong believers in test-driven development and in continuous delivery. So for test-driven development, we do this because tests help us to go faster, right? We're making an investment up front in writing tests as we write our software, but we do that because the tests have our back, right? They're there to let us know when something is broken because of a change that we made. And it actually ends up increasing our development velocity rather than slowing it down. Tests help us make better code. So it gives us the confidence to be able to break things, and it gives us the confidence to be able to refactor in a very courageous way when we want to do something different with the code. And finally, tests make better systems. So it allows us to catch bugs earlier, and it allows us to fail faster. So the other, test-driven development has been practiced by a bunch of people for a long time, but widely in the industry relatively recently. So often you will hear from managey types, and I have become this person, so I'm sad. But you often hear from managey types that we don't have time to do it right. And I say wrong. I say we don't have time to do it twice. So if we do it right, at least right enough the first time, as Brian Cantrell also said in today's keynote, then we're going to be in a much better position to build on something solid that already exists and be able to move forward in a great way. And in fact, this is maybe counterintuitive, but the more constrained we are in terms of time and resources, the more important it is to build right the first time, right? If we don't have much time and we don't have much resources, we should spend our time building a small number of really great features rather than a large number of sort of half-implemented ones. And just to be clear, when I say right, I don't mean perfect, right? You build the 80-20 rule of the thing that you actually need to get done, you do it well, high quality, move on. The implication that has for us at Stitch Fix is a really interesting one. It's the first time that I've been in the industry for a long time, as you can tell by looking at me, and we basically don't have a bug tracking system. So bugs are fixed as they come up. So we have a system that shows us the bugs that are happening in real time in the applications, but when they come up, we fix them. And we have a really solid system from then on. We do, of course, have a backlog. It's not like we don't know what we're going to do next week, next month, or next quarter. We have a backlog, but those backlog are new features, right? Features we want to build, technical debt that we want to repay. It's not a whole list of things that are broken in the current set of features. Does this kind of make sense? Yeah. It's really cool, and I really love working in an environment like this, which is why I bring it up. So the other angle about processes and practices is continuous delivery. So most of our applications at Stitch Fix are deployed multiple times a day. And when I used to talk about stuff at eBay, when I first started giving conference talks in 2006, I was talking about the eBay architecture and some of the practices at eBay. And it was the first time that eBay had sort of opened the kimono and talked publicly about what they were doing. And so one of the things we talked about beyond the architecture was eBay used to release the site on 2-week trains. So they would release the entire site once every 2 weeks. And just to give you a sense of how far we've come, 11 years ago, that was amazing. People were like, oh my God, you release the whole site every 2 weeks? And now if I said that at this conference, people would be like, oh my God, you release the site every 2 weeks? So we're doing it multiple times a day. This leads to more solid systems, right? So it allows us to release smaller units of work. It means the small units that we release are faster to repair, easier to diagnose if they go wrong, and they're smaller changes that, for us to be able to roll back or to roll forward. And it also enables us to do really rapid experimentation, small experiments that are really cheap, so we can do A/B testing and ABC testing and ABCD testing. Because it's cheap, we are able to rapidly iterate and experiment really quickly. And I bring this up because that's going to be super relevant to the data stuff that I'm going to talk about in a moment. But the last sort of pillar that we're built on is the cultural aspects of DevOps. And what that means to me is end-to-end ownership for a team of the service. So a team owns a service from design through deployment all the way to retirement. And the team is responsible for all aspects of the service, right? Not just the features, but also the quality of the service, the performance of the service, the operations of the service, and the maintenance of the service. It's basically the reification of the Amazon idea of you build it, you run it. Okay, so that's the background, and now I want to take the rest of the time to talk about microservices, some of the ways that we've approached the problem, some of the things we've learned in migrating our monolithic database into individual services, and also some patterns and practices that you can take back as you're trying to maybe migrate your monolith in the same way. Okay, so, but first, it can be easy to think that at a conference where there are lots of talks about microservices that we would be saying, you know, you should do microservices for everything. That's absolutely not true. And I'll give you some great examples. In fact, there are examples from places you've probably heard of. So at eBay, depending on how you count, it's on its about 5th generation of its architecture. So it started famously as a monolithic Perl application written over a 3-day weekend by the founder in 1995. So he wanted to play around with this new web thing and try it out. And he was a devotee of economics, and he was like, well, I'll build an auction site. He totally was not planning on building a business. This was like a fun little hack. Not hack day, like hack 3 days, hack long weekend for himself. But it ended up becoming a business, and you know, now he gets to live in Hawaii and stuff, so that's pretty cool. So the next generation of eBay's architecture, the V2 of it, was a monolithic C++ application, and at its worst, it was 3.4 million lines of code in a single DLL. Yeah, don't do that. You want to talk? You think you have a monolith? Yeah, 3.4 million lines of code in a single DLL. Oh, and they were hitting the compiler limits on the number of methods per class, which is 16K. So seriously, don't do that. Okay, the next iteration, V3, was a re-implementation in Java. And it wasn't microservices, but you can kind of think of it as mini applications. So take a page or a series of related pages on the site, like the buying part, the search part, the selling part, et cetera, and make a Java application out of that. And then there were a bunch of shared databases underneath. And then the final iteration of eBay's architecture and where it is today is you could basically describe it as a set of polyglot microservices. So Twitter has gone through a similar evolution. So depending on how you count, Twitter's on about its 3rd generation. So it started famously as a monolithic Rails application, which my friends at Twitter tell me they call the monorail, which that's a clever name. The next iteration after that was breaking out a bunch of the front end into JavaScript, a bunch of the back end into services written in Scala, and then now it's fair to characterize Twitter as a set of polyglot microservices. Amazon has gone through a similar evolution. So Amazon isn't so clean on the divisions between their architecture. They went wide relatively early. But they did start out with a monolithic Perl C++ application. which actually you can still see in some of the product detail pages if you go to Amazon. If you ever see Obidos, O-B-I-D-O-S in the URL, that was the name of that original monolithic application. And of course, for search engine optimization, like they don't want to change the pages because of PageRank, and yeah. Anyway, so they started to break up their backend into more service-oriented architecture, lots of services written mostly in Java and Scala, and now I think it's fair to characterize Amazon as a set of polyglot microservices. So there are two things to take away from this. One is all these places didn't start out doing microservices, but all of them ended up doing it. Does it make sense? So when you're starting out and you're still trying to figure out whether there's a business model and whether you have product market fit and whether you're delighting your customers, this is not the time to build a distributed system. Later on, when you've reached massive scale, that is the time. Okay, so now that we've sort of put microservices in a bit of an architectural evolutionary context, what is a microservice? So to me, the micro of microservice is not about the number of lines of code that's in it, but it's about the size and scope of the interface. So a microservice is single purpose, it has a simple, well-defined interface, and it's modular and independent. And if this looks like good, just simply good encapsulated class design, you're right. That's exactly what it is. And if it looks like this is the right way to build services, and why did we need to say micro, you're right. As far as I'm concerned, microservices are nothing more than service-oriented architecture done properly. But the other element of microservices, which is where a bunch of the initial SOA re-architectures went wrong, is a critical element of a successful microservice is that it has isolated persistence. In other words, the microservice, the only way to get the data in and out of a microservices database or whatever persistence mechanism it uses is through the published interface. Does it make sense? That's isolated. There's no backdoor way to get into the database from the outside. How does that work, Randy? I'm glad you asked. So I'll give you a couple of patterns or a couple of approaches to how you might be able to do persistence in this way. So the approach number one is that the team that builds and operates the microservice also operates its own data store, right? At Stitch Fix, we use Postgres as our backend, so we have a bunch of services where the team is essentially maintaining its own instance of Postgres. But you could replace that with MySQL or whatever persistence mechanism you like. Another approach is to use a persistent service, right? So store to your own tables or your own space within a persistent service operated on your behalf by maybe another team at your company or maybe a third-party cloud provider like Amazon Dynamo or Relational Database Service or Google Spanner or something like that. And the idea here is it would be operated on your behalf. So you don't need to know how to scale and tune the persistence mechanism, but the key thing that you want to have as a service owner is that your slice of that multi-tenant system is yours, and it's isolated to you and nobody else can get in there. Does this make sense what I'm talking about? Yeah, nods, good. All right. And again, the critical thing that we're trying to get here is the only external access to my data store of my service is through my published service interface. So speaking a bit about interfaces, I want to talk a little bit about how to evolve interfaces in a microservices world. So a lot of people have maybe worried about, well, how do I version microservices, and isn't this really complicated? And it takes a little bit of discipline, but it's actually not as complicated as you might think. The key element that you want to have here is you basically, as you are developing and evolving the interface of your service, you just simply want to make sure that the changes that you make are both backward and forward compatible. And the main goal here is that you want to make sure that you never break your client's code. But Randy, you say to me, sometimes I need to make breaking changes. Sometimes I need to make iterations on the interface. Great. So the way to think about that is something called semantic versioning, which probably most of us have heard about. So the semantic versioning is like major version, minor version, patch. Major versions are for breaking changes. Minor versions are for additions that changes in behavior, like adding new methods. And patches are for things that don't change behavior at all, but are just sort of improvements in bug fixes or performance or something like that. So often, if you have a situation where you want to do breaking changes to your interface, you're often maintaining multiple interface versions of your service, and that actually might mean maintaining multiple deployments. Does it make sense? So if I want to go from version 10.whatever to version 11.whatever, my team, the service team, might be maintaining, or would be maintaining an instance of version 10 and an instance of version 11. And if I do that, What I want to have is a pretty explicit deprecation policy with the clients that are using my service. In other words, I want to go to those clients and I say, look, the new version is version 11. I'm going to keep maintaining this for you for, I don't know, 3 months, 6 months, whatever is the friendly thing to do within your company. But notice that the DevOps idea that I own and operate the service myself forces me to have a really strong incentive to help my customers wean off of version 10 onto a version 11. Does it make sense why I'm saying that? I'm maintaining both version, as long as there are customers that are clients of mine that are still using version 10, I have to continue to maintain it and continue to operate it. But as soon as I can get that last client off onto version 11, then I can shut it down and we're good. So I and my team have a really strong incentive to invest in helping customers to move from version 10 to version 11. Does this make sense what I'm talking about? Cool. All right. So the next thing about data in microservices, or sorry, the next thing is about extracting microservices from a monolith. So at Stitch Fix, we build most of our applications in Rails, and we have a bunch of backend services in Go. So Rails really wants you to build a monolithic application, and thankfully we avoided that temptation. So we have about 40 different applications for different areas of our business and different functions of people in the different areas. But our version of the monolith problem is we did build a monolithic shared database. So I'm not sure you can, well, I guess you can see better than I can see. But basically it has all the interesting entities of our system, right? So the shared database at Stitch Fix has information about clients. It has information about items, shipments, which are those fixes or boxes that we send out. It has information about the metadata information about the styles and SKUs that we sell and have in our inventory. It has information about our warehouses, et cetera, et cetera, et cetera. And so all the different, all the 40 different applications, more or less, are using information in this shared database. Obviously, this is a single point of failure. This is a single performance bottleneck. It's kind of a challenge as we go forward to being able to move really fast in parallel and get the real benefits of those small teams, the continuous delivery, et cetera. This is a bottleneck that slows us down. So we're going to try to get rid of it. And I'll talk through the pattern of how we're approaching that. So the goal here is to decouple applications and services from the shared database. So I'll take a little bit smaller example. Like let's imagine, just so that there won't be so many boxes and lines on the screen. So let's imagine we have 2 applications and 3 tables in the database. So the first step is that we want to create a service for, let's say, clients, right? So clients were a thing that we have in a table in the shared database. So first we create a client service. Then we have the applications that used to be directly talking to the table now talk to the service. And now we extract that table from the shared database. And now we have a standalone service that's not dependent on the shared thing. And now we just keep doing that over and over again. So we rinse and repeat, as we like to say in America. So we create an item service on top of the core items table. We create a style service on top of the SKU table. And now these are our new microservices, right? So we can now draw boundaries. These are, the real extent of the microservice is this interface boundary that surrounds the application, sort of business logic-y part of the service, and the database. Does this make sense? Simple steps. Now, I showed you that in like, whatever, 1 minute, and you might have thought that I was making it seem like it was easy. It's not at all easy, right? What's hard is uncutting the links between, the joins and database transactions that are dealing with those individual tables. So there's actually quite a lot of work associated with this. But once you have sort of decoupled it, you can follow through this this pattern or this sort of pipeline of work that I just laid out. Cool. Okay. So now I want to talk about some ways of dealing with data in microservices, and again, patterns that we have found to be really effective at Stitch Fix and things that also we have done at Google in the past as well. Okay, so one thing is how do we deal with shared data, right? So in our monolithic database, there are a bunch of tables that are used in lots of different queries and in lots of different applications, and how do we deal with that? So the problem here is that the monolithic database makes it really easy to get access to the shared data, right? I can just join with it in a select statement. I can query it in applications that are using the database. And so the question is, where does that shared database go in a microservices world? And the principle here is that there should be, for any piece of data, a single system of record within the overall ecosystem. So every piece of data is owned by one and only one service. Okay, now that service implementation probably has replication and so on. I don't mean a single machine, but I mean a single logical service that's the responsible party for that particular piece of data. And that service is the canonical system of record for that thing. So there's one, in the ideal microservices ecosystem that we are moving toward at Stitch Fix, there will be a service that owns clients, another service that owns items, another service that owns orders, et cetera. Every other copy of that data in our system, every other place that we represent a customer or an item or whatever, is a read-only, non-authoritative cache. Take a moment to let that sink in. Does it make sense? There's one place where I can update it, and that's where it actually lives. Any other place that remembers anything about items is just a cache of that thing. So if you keep that in the back of your mind, now the approaches that I'm going to suggest are going to make more sense. Okay, so the first approach is kind of just look up synchronously, right? I want to find information about, what's the example here, about customers, and so my order service needs information about customers, like maybe it needs the address to know where to send the order or something like that. So the idea here is that the customer service is the system of record for customer information, and the order service synchronously calls into that customer service in real time. Does it make sense? This is pretty simple. Okay. The second approach is leveraging more event-driven techniques, like we saw in the keynote yesterday from Martin Fowler. Still the customer service owns customer data, but instead of the order service calling in a synchronous way to the customer service, maybe the order service needs to do some complicated stuff with the customer information, and needs to have a cache in order to do that efficiently. So let's imagine that the customer service sends events when customers have changed. So send something like customer updated event. The order service is listening to those events, and the order service then takes that information and caches it locally, and then it can now use it to do its fancy stuff. Does this make sense? So the pattern I'm calling asynchronous event plus a local cache. And recognize that if I ever asked the order service about the state of a customer, it would be wrong, right? It would be potentially stale. And by the way, the order service should never have an interface like I just suggested, but all the information in the order service about customers is potentially slightly stale. Okay. And then approach 3 is for data that's relatively immutable, and we have a lot of this at Stitch Fix, right? It's sort of immutable read-only metadata like size schemas, so that's a thing like numeric sizes for women, right? Size 2, size 4, size 6, et cetera. Small, medium, large, extra large, for other types of sizes. That's a size schema. And that's a thing that doesn't change very often, right? It's rare to have some new, extra, extra, extra small or something like that. Colors are a similar thing for us. Fabrics, the US states, right? I hope to God there's nobody who implemented a microservice that serves up, what are the values of the US states. But yeah, so don't do that. So how do we deal with that? Again, we do a lot of these application stuff in Ruby, so that's why I have the little gem diagram, gem icon there. But if item service needed information about, I don't know, colors, and then style service needed it, and receiving service needed it, this would just be a shared library. Does this make sense? Cool. Okay. So those are the choices that we have around shared data. And what I am not telling you is that one of them is better. We actually use all of those techniques at Stitch Fix for various things. It totally depends on how often the data changes and what the use case is. Okay, so now I want to talk a little bit about events. And I want to talk about events now because that's going to give us another set of tools to do the next set of patterns that I'm going to talk about afterward. So I am a strong believer in the thing that Martin said in his keynote and didn't get a laugh even though he totally should have, which is events are a first-class construct in programming, and we don't take advantage of it as much as we really should. So if you ask Wikipedia, an event is a significant change in state. So it's basically a statement that some interesting thing has happened in our system. And it might be that, when I produce an event, it might be that nobody's listening, it might be that one consumer is listening, and it might be that many consumers are listening. But the idea is that the producer produces the event, and typically consumers are subscribing to that event and updating themselves or doing something interesting based on the event being propagated. I strongly believe that events are the underappreciated, redheaded stepchild, fourth fundamental building block of building big systems, right? So we all know the three-tier architecture where there's a presentation layer, an application or business logic layer, and a persistence layer. I think we should add to that a first-class concept of state changes in the form of events. And this is intuitive, right? Events represent how the real world actually works. Right? So if you think about finance, when Deutsche Bank and Bank of America are trading currencies, like they're not doing a distributed transaction, right? They are producing a bunch of events on both sides sort of at each other, and then they reconcile at the end of the day. I was trying to, as I was putting this talk together, I was racking my brain to try to think of what's a really visceral example of events in our own lives. Well, here's one. How about the actual software development process? So I'm a big fan of continuous delivery, but raise your hand if every time you press enter in your IDE that it gets deployed to production. Does anybody do that? No. So, because that would be crazy, right? That would be totally crazy. So when I hear people say it is hard to reason about systems where something happens in one area of the system, but it hasn't yet propagated to another, and how do I deal with that? Just think about what you guys do 8 hours, 10 hours, 12 hours every day. Does it make sense? Yeah. And anything that you call a workflow, that is exactly a set of events. Does it make sense? A workflow is a thing that I do that produces an event, and then there's another thing in the workflow, another thing in the workflow, et cetera. Okay, so I'm going to use this as a building block, as I just said, to build some interesting things that we can do with microservices. So events in microservices go very, very well together. So just like the synchronous part of our interface, events are a first-class part of the interface of a service. So a service interface includes the obvious stuff, which is like the synchronous request response part of it, right? So whether it's REST and JSON or gRPC or whatever thrift, your request response is like, that's the obvious part of the interface. But any events that your service produces, any events that your service consumes, those are also first-class parts of your interface. And also any bulk reads and writes that you do into or out of your persistence mechanism, like for ETL purposes or analytics or something like that, those are also part of your interface. So again, I said this before, and I'll sort of say it again because it's so important. The interface of a service is any mechanism that gets data in and out of a service. Does it make sense? Cool. Okay. So now that we have events on our microservices, now let's put that together and do some fancier stuff. So joins, right? When I have a monolithic database, joins are super easy. So the problem here is that I get used to that, right? So all I have to do is edit the from clause in my SQL statement, and magically I've joined together a bunch of tables in a bunch of different entities in my system. When I split those tables up into separate services, this becomes a lot harder. So I'm going to give you some techniques to deal with it. So the first approach is a service that materializes that join or materializes that view for you. So what do I mean? Let's imagine that I want to produce something like an item feedback service. How did people at Stitch Fix feel about items and the items that we sent to them, pieces of clothing, and which people did we send them to? And let's imagine we're going to use that for some algorithmic purpose later on. So the way that we would do that is the item service is going to produce events when items are updated or added in the system. The order service is going to produce updates and events about orders changing in our system. And we're going to be accumulating that in our item feedback service and basically denormalizing the join between items and orders. So in this model, we're not doing the join in real time at query time. We're doing the join, we're reifying, we are denormalizing the join ahead of time. Does it kind of conceptually make sense what I'm talking about? Yeah. So the idea is that we're maintaining a denormalized join of items and orders together in our local storage, in our own little database or whatever for this service. And you use this technique when you have a really high number of rows on each side. So it's called high cardinality in database terms. So if I have a lot of items and a lot of orders for those items, this is a great thing to do. So if that seems really weird, what I just suggested, I want you to take a step back and think about that actually there are tons of systems that you use that do this exact technique. So almost every NoSQL approach approaches things in this way, right? In relational databases, we make it super easy. We write individual things, and then we reconstruct things together at query time. And for most NoSQL approaches, the way that you do it is you actually compute at write time the queries that you want to run. So you can't run arbitrary queries, but you compute at write time, and you do the denormalization at that point. And that's exactly the technique that I just described. Another example is the wording that I actually used here. So lots of database systems, Oracle, et cetera, have a concept of a materialized view, right? Maybe it's really expensive to join items and orders together because there are so many. And so what you tell the database system to do is like maintain that view for me, denormalized all the time, and let me query it quickly. Search engines work this way, right? So anybody who uses Elasticsearch has this tool in their toolbox. Analytic systems definitely do this, right? Any data warehouse or analytic system uses this technique. And actually log aggregators, right? Things where you bring individual logs together, that's also a join like this. Is this making sense? Feeling more familiar on this slide maybe than last one? Okay, cool. So here's the next technique. The next technique is to just simply join at runtime, right? So join in the application or whatever client service you're using. So let's imagine that the use case here is I want to show an order history page. So I want to show to one of our customers all the orders that they have, plus some metadata about themselves, like maybe their name or how many boxes we've sent them or something like that. So the idea is we're going to first query over to the customer service and get the customer record for this particular customer. Then we're going to query over to the order service, and we're going to say, find me all the matching orders for this customer. Right? Super simple. Does this make sense? Yeah. And how we would do this in a monolithic database, this would just be a join with two tables in the from clause. You're all good. Now we're just doing that join in the application. Right? We're just simply going one place to get one half of the join, another place to get the other half of the join. And this technique, as distinct from the previous one, is best for cases where I have a single customer, so a single on one side of the join, and multiple orders on the other side of the join. So in database terms, the last one was M to N, and this is a 1 to N join. Does this make sense? Cool. I'm sure this seems pretty familiar to people, but if it didn't, you do it all the time. Any web application that goes to one that is like constructing a page out of two different sources of data does this, right? So if you display a page that has anything more than one query, typically you're doing a join like this, right? You're going one place to look up one piece of information, one entity, and you're going another place to maybe get the detail or look up another entity that's related. Does this make sense? Cool. All right. We're going to step it up one notch. So I want to talk about workflows and something called Sagas. So the problem here is transactions, right? Transactions are awesome. They are so fun and so easy and so, well, easy. A monolithic database makes transactions across multiple entities trivially easy. That's one of the great things about databases, right? So if you're using a relational database, you get ACID transactions. I can update a customer record and all of her orders at the same time, all in one transaction, and it's easy. Once I have split those tables into separate services, this is really hard. So the answer is very much not do a distributed transaction with a two-phase commit. Please don't do that. That'll kill your scalability and be a real performance bottleneck. But still, you want to have this thing happen all at once or not at all, right? That's the A in ACID. I want to make sure that at the end of the day, I update the two entities at the same time, or I don't update either of them. Okay. So the trick here is that we want to turn that transaction, that super easy transaction, into a slightly more complicated but more scalable thing called a saga. So a saga is a bunch of steps connected by events that are basically a state machine. So we're going to model this transaction across multiple entities as a state machine of individually atomic events. And once we do one event, we're going to do the next part of it, we're going to do the next part of it, and we're going to do the next part of it. Okay, so the idea is to re-implement this thing as a workflow. So let's imagine we originally wanted to update A's and B's and C's all together into single atomic transaction. In a distributed microservice world, you can't do that in one go, but you can, at the end of the day, at the end of this workflow, make it happen or not happen. So the idea is you update the A, it sends an event, that updates. We're going to update the B, that sends an event. We're going to update the C, that sends an event. We'll update the D. You get the rollback by doing what are called compensating transactions or compensating operations in the reverse. So if we had a failure along the way, we would send events to kind of back through this chain, back the other direction through the state machine, and kind of undo the stuff that we needed to do, right? So we remove all the Ds that we added or tried to add. Then that sets events, and that's going to remove all the Cs and remove all the Bs and remove all the As, et cetera. Does this at least conceptually make sense? Yeah. It's way more complicated than a database transaction. I'm not going to tell you otherwise. But it is at least an existence proof. This is a thing that you actually can do. This is the way that you can get the kind of transactional characteristics or something similar to transactional characteristics when you're in the microservices world. So again, I want to bring this back to something that's maybe more visceral for people. So if you think that no system works the way I just described, not true. There are actually a ton of systems that work this way, and they're really complicated. And basically anything that you talk about as a workflow works the way that I just described. So payment processing, right? It starts with, please take $50 out of this customer's credit card and put it in our account. There are a lot of steps that go into that flow. Those steps are not done in a single, immediate, atomic database transaction, right? We do not go across all the different credit card issuers and banks and acquiring stuff and all that kind of stuff. That does not happen as a transaction. That does happen as a workflow or a series of steps or saga of individual things connected by events. And anything where we're talking about approving something, like an approval workflow, like an expense report maybe in your company that flows through, it needs to be approved by X person, then Y person, then Z person. This is exactly the same thing, right? And if somebody at the end of the chain or at the highest level of the chain says, nope, Randy's expenses, like that, that jazz club, sorry, that's not something that we cover. More's the pity. Okay, so that goes back down to the chain and gets rejected all the way down. And maybe if I can convince my boss that no, there actually was a business purpose for my going to the jazz club, and yeah, then maybe it can go back up again. Does it make sense? Yeah. Yeah. Okay. Cool. So this talk would not be complete without at least a nod to serverless. Right? So one of the maybe obvious use cases for serverless techniques, functions as a service, is exactly the thing that I just described. So an ideal use of functions as a service, or what we're calling serverless, is this super lightweight processing that we do in that chain of events in one of these sagas, right? So let's imagine that A does its operation, B does a little bit of processing, and then sends another event, C does a little bit of processing, et cetera. Those are super lightweight logic. Those are probably examples of 10 lines of code, 20 lines of code, really simple if you get right down to what the logic is. They are stateless, right? They are triggered by an event, and then they do their operation, and then they produce other events out the other side. And so they're perfect for something like Amazon Lambda or Google Cloud Functions or something like that. Does this make sense? Yeah. It is obvious, but let's just say out loud, microservices are not the answer to every problem. Serverless is not the answer to every problem, but these are just tools that we have in our toolbox. And a healthy company now and in the future is probably going to be combining techniques that use microservices for a bunch of stuff, use serverless or functions as a service for a bunch of other stuff. It will be possible to do something all in, let's say, functions. In the serverless track yesterday, there was a great example from one of the presenters about they built this whole company and his whole e-learning system around events. That's awesome. But the vast majority of systems are going to be a combination between different techniques, just like they are today. Okay, so I want to, running out of time here, so I want to just sum up a little bit. So again, modern software development, doing things quickly and effectively in a highly data-centric environment like we have at Stitch Fix. So for organizations, I strongly recommend that the way that we move quickly and efficiently is with small teams with well-defined areas of responsibility in terms of processes and practices, test-driven development, and continuous delivery. In terms of culture, a DevOps culture of ownership, and you build it, you run it. And then finally, leveraging the tool, at least at a certain scale, leveraging microservices as your technological approach here. So thank you very much. I would be remiss if I didn't let everybody know that Stitch Fix is hiring. So those 75 engineers, we're hoping to grow a bit more. The link is here. We are hiring in application development and data science and platform everywhere. We are based in San Francisco, but actually more than half of the engineers on my team are remote, and they work from all over the United States, sometimes from their houses, sometimes from smaller offices that we have in other parts of the country, like Pittsburgh and Austin. So feel free to grab me personally. While I'm here, I'll be here for the rest of the day. You can tweet at me at Randy Shoup or connect with me on LinkedIn. We'd love to, if any of this stuff sounds really interesting, you want to learn more about it, I'd be happy to talk with you. So thank you very much.